So, I'm going to be doing a talk, and it's an intro to NFC, near field communications. Very quickly, a bit about me. My name is Robert Portvlie. I'm a senior consultant with Foundstone. Spoke here last year. Brad Antonowitz and I did a talk on war driving the 4.9 gigahertz public safety band.
That was awesome.
Thank you. I really did think a lot to me. So let's see, what do I do? I'm a pen tester. I do network wireless web app pen testing. I kind of have like a focus on wireless. I keep trying to get away from it, but I keep getting dragged back in, like Michael Corleone. I teach Foundstone's Ultimate Hacking Wireless class. I've taught it at Black Hat the last 3 years. And I do a fair bit of wireless research in my spare time. I'm a fairly frequent contributor to the Open Security Research blog. If you guys don't get a chance to read it, you get a lot of really good contributors to it, and there's a lot of really great stuff on there. And if you guys want to, ask me any questions, my email's there and my Twitter address. So feel free. I'll put it up again at the end. Always happy to talk wireless stuff, so feel free to ping me anytime, and you may get more discussion than you want. Sometimes I just don't know when to shut up. On that note, we'll move forward. So what we're going to talk about is we'll do a little bit of an intro, to basically what's NFC, how do you use it, what's it used for practically, a little bit about the protocols involved. Then we'll talk about what hardware is involved in terms of the chipsets, secure elements that are used, and also what NFC adapters would be most useful to you to do some NFC hacking, right? Then we'll talk about some of the software that's used for said hacking, and then some of the attacks that have been done so far against NFC. So what is NFC? Near field communications. Basically, it's a set of standards for communicating between either two mobile devices, generally would be mobile devices, or a device and a tag, or actually a mobile device acting as a tag, where, in the interest of mobile payments, as we were just discussing, you would hold your phone up to a NFC reader at a Starbucks or Home Depot or what have you, and the reader would read your card and access your bank account, read your phone rather, access your bank account, and you'd be able to make a payment. As you can see, it's very short range. I heard claims of 10 centimeters, but typically you're probably under 4 centimeters, probably closer to 2. When you transfer data between two mobile devices, typically you'll place them back to back, touching each other. The frequency is 13.56 megahertz, which is the high frequency band in RFID. It's also used by the NXP MyFair, which is actually MyFair built mostly on the NFC's compliance standards. Things like Visa's Visa's PayPass, e-passports, and HID's iClass cards, which actually fall under what's known as NFC-V or NFC vicinity. These are access control cards for getting into buildings and such. You can also see the data rates are fairly slow, 106, 212, or 424 kilobits per second. Generally, what it's not a rocket ship in terms of bandwidth. Generally, what you're doing when you're doing data transfer between devices is NFC is used to bootstrap some other kind of protocol, typically like either Bluetooth or Wi-Fi direct, and then do the data transfer over that. We'll talk a little bit about that. The NFC Forum is who maintains the NFC standards. NFC Forum is formed in 2004. It's a consortium, I guess you could say, of Nokia, Sony, Samsung. Those are the founding members of the family. And now has over about 150 member companies. So basically, they're who lays down the standards specific to NFC. Although, as we'll see, there's a bunch of other standards that NFC is built on, like ISO 14443 and some others. But the actual 18092, I believe it is, standards are all laid down by NFC Forum. Okay, so some of the uses for NFC. One of the big ones that you hear a lot about now are contactless payment systems. Some of the players in that space are Google Wallet, with Google, obviously, and ISIS. ISIS is a competitor of theirs. This was rolled out, or is in the process of being rolled out by Verizon, AT&T, I believe Bank of America. Who's the other one that was involved? One of the other banks. Capital One actually just bailed on them. We'll talk a little bit more about that in a bit. But if you can think of one of the reasons that mobile payments are not more prevalent, first of all, mobile payments, if you're not familiar with them, like I said, is your device acts as an NFC card or RFID card. And you hold your device up to a payment kiosk, or a reader rather, and your bank account or credit card account is accessed through the reader and verifies your payment. One of the reasons that you do not see that it hasn't made more progress in the U.S. is the fact that you have these two competitors. And you have a scenario where Verizon is actually, and AT&T were blocking Google Wallet, Google from getting the Wallet app onto their phones. They were also blocking, or denying, Verizon was, denying Google access to the secure element in their devices, which is a secure integrated circuit. It's almost a computer within a computer. It has a processor, an operating system, and RAM, and that's secure. You need cryptographic keys to access it. A lot of Android phones now have an embedded version of these. We'll talk more about these later. But anyway, this is where the important stuff would be stored. Your credit card or numbers, or your bank account numbers, or what have you, things you don't want people to get a hold of. Would be stored in there. So to really do secure mobile payments, you want to use one of those. Well, Verizon said, well, we can't just allow you access to this, and security involved here. What? No, we're not. Our own payment system? Well, that has nothing to do with that. You're being silly. At any rate, so that sort of fracas between the players in this space is why it hasn't gotten, it was one of the main reasons it hasn't gotten further than it has so far. It's basically, they don't want it to get, widely implemented before they get their piece of the pie, and a significant amount of money is at play here. Samsung's in the mix there too. There's a lot of companies, that are jockeying for position in there. We'll talk more about that a little later. So anyway, data transfer between devices. As I said, NFC is typically used to actually bootstrap another kind of protocol because NFC is so low, such a low transfer rate. Typically Bluetooth, which is Android Beam. I'm sure you guys are familiar with that. But on the Samsung devices, like my S4, they have what's known as the Samsung S Beam, and in that case, you're using NFC to bootstrap a Wi-Fi direct connection between the devices, which actually allows for a higher transfer rate than Bluetooth. Reading NFC tags. So pretty much just like regular RFID tags, but generally you'll find them to be formatted to the NDEF format, which is the NFC data exchange format. But basically you have a tag and you read the tag with your phone. This is used in a variety of places, commonly used in what's known as smart posters. So you have a poster or some kind of sticker or whatever, for an advertisement for a company. You put your phone up against it and it launches their web page, or it may launch their app or download their app onto your phone, or perform another function on your phone. There's a number of things that can be performed on your phone by reading an NFC tag. One of the things you can do, I can think off the top of my head, is not polite to burp in the microphone. For instance, I've known some people that when you walk into their house, they'll have an NFC tag. You read the NFC tag with your phone, and it will add the SSID of their wireless network in their house to your phone, along with the WPA pre-shared key or what have you, and everything else you need to be able to access their guest wireless network. So you can see you can perform fairly significant actions on your phone. One of the other things, not besides NFC door locks, you see these getting quite, you see quite a few of these now. I don't know about their popularity, but there's several different vendors that have them, and basically you can use an app on your phone to unlock your house by walking up to the device. They're typically multi-protocol, meaning you'll see ones that are NFC enabled. They'll also be enabled for, say, Z-Wave and Bluetooth and or Zigbee. not cheap, like around $300 starting. But, pretty cool stuff. Definitely fun stuff to hack on if you're into wireless hacking. The other thing in that space that's even a little more interesting is NFC, on the end of using your device as a tag or as a card, is some vendors like HID are offering systems like HIDS COS, where your phone acts as a HID I-class vicinity card or building access card. So instead of using a card that you normally use to gain access to your office, you hold your phone up to the reader and it verifies you. This once again uses the secure element in the card. In their case, it's an SD card based secure element, and is verified against the back end system. So yeah, that's pretty cool. And hotels are doing this as well. The Aria in Las Vegas has a card-based system right now, which is regular NFC contactless cards. But what a lot of these hotels are looking to do in the future is you go to the hotel, you check in, you'd have an app on your phone from them, and it would provision your room keys right into your phone, ostensibly stored in a secure element, if it was to be done in a secure manner. But regardless, provision to your device, and then you go up to your room, you open your room with your phone. So that's something else that's being tested at this point. I don't know of any actual implementations of it, but they are looking to do that. Okay, so mobile devices. As you can see here, very prominently figured here are the Android-based devices. iPhone still does not have it, although it's been widely speculated that the iPhone 6 will have it, although there's been, as far as I know, no confirmation from Apple on that. There was also some speculation the iPhone 5 would have it, but at this point, I would imagine that they would not leave this out of the next version. It's been in the Nexus since the Nexus S, so it's the Galaxy and Nexus series since the Nexus S. The first phone to have it was actually a Nokia phone. A Nokia device was the first phone to have NFC in it. But since then, you can see that the Nexus and the Galaxy Nexus series, or Galaxy series, all have had NFC enabled in them. Mostly up until now, they were using NXP chipsets. The Nexus S had the NXP 544, I believe, in it, and the Galaxy Nexus, which is probably one of the best phones for NFC hacking, had the PN65 NXP chipset. As of the S4, the Galaxy S4, they were actually also using NXP's NFC stack in the phones. So NXP had a really good thing going with Samsung, but for whatever reason, as of the S4 now, they are using a Broadcom NFC chipset, and the secure element in the devices is a secure element from Inside Secure, and they're also using Inside Secure's NFC stack now too. So apparently a bit of a falling out there. As we'll see later, one of the advantages, at least having an NXP chipset, is some of the tags, I guess you could say, in use like NXP's MyFair Classic, don't fully implement the standards. So if you don't have an NXP chipset, you can't read those cards. Okay, so some of the standards involved. We have ISO IEC 14443 A and B. The main difference between type A and B is the modulation and bit encoding in use. We'll talk in a minute about what level of the radio of communication takes place and what parts of the standards. But GIS-X 6319, that's the Japan Industrial Standard. That's Felica. That's a Type 3 card. That's Sony's standard, or Sony's product. ISO IEC 18092, that's also known as NFC IP-1, which focuses specifically on peer-to-peer communication between two mobile devices. So that defines that that part of the standard. And then we have ISO IEC 15693, which is the standard for vicinity cards. It's not really NFC, but it is. It's known as NFC vicinity. And it's mainly for access control cards for building access. It's got full support in Android. So it's one of the, as we'll see, one of the standards in order to implement Android, implement NFC in Android as per Google's standards for the Android open source project, you must support NFC-V. But depending on what chipset you have in your phone, it may or may not work with different types of cards that fall into that space. So there's a lot of, as you can see, there's a lot of different standards involved, and some vendors take all of them or not all of them, and sometimes there's not quite the interoperability that you would hope. So sometimes it's, it's a little bit of a crapshoot as to whether, this tag is going to work with your chipset and so on and so forth. Anyway, a little bit more about ISO 14443. -1 specifies the physical characteristics. -2 specifies the radio frequency, power, and signal. -3 specifies initialization and anti-collision. And then 4 would specify the transmission protocol. Now, this is where some vendors, like NXP with their MyFair Classic, and also the MyFair Ultralight, I believe, divert from the standard. And in the case of the MyFair Classic, NXP was utilizing their own cryptographic exchange called Crypto One. In-house crypto, always wicked secure, right? Not so much. So that thing's been riddled full of holes in the past 5 years now. It is, pretty much, it's the NFC equivalent of WEP. It's, don't use it for the love of God. Okay. All right. So how does NFC work? So NFC falls into the 13.56 megahertz range, which is the RFID high frequency band. It is one of the RFID technologies that uses inductive coupling. What is inductive coupling? Well, inductive coupling is the reader generates a magnetic field and then thereby powers the tag with that magnetic field. As a capacitor in it that's powered by the reader, and then to send data back to the reader, the tag modulates that field, and thereby sends the data that the reader is requesting. Use amplitude shift keying for modulation by and large, anyway. From the PCD to PIC. The PCD is the payment proximity coupling device. That's the reader. PIC is a proximity integrated circuit card. I almost forgot something. And that is a card. All right. So those are the two terminologies. But anyway, from reader to card, it uses a modified Miller encoding. It modulates at 100%. So like a 1 is 100% a signal, and a 0 is like pretty much nada, at least on top of the carrier wave. There's an edge case of that. A PCD transmitting at 106 kilobits will use modified Miller at 100%. The PIC to the card to reader rather uses Manchester encoding, not modified Miller, and will modulate at 10%. The reason for that being that you're obviously don't have a lot of power when the tag is being powered by the reader. And so in order to be somewhat conservative on that, you're only going, so now a 1 is 100% of the signal, and a 0 would be 90% of the signal. So you can eavesdrop on this pretty easily and see this using oscilloscope and probes. However, it's a lot easier to read from reader to tag than it is to read from tag to reader because of the way that the wave form looks. All right, so 3 modes of operation. Reader writer, again, the device, your mobile device will act as a reader and read a card. All right, peer-to-peer, you have 2 devices will exchange data in a scenario such as Android Beam or Samsung's S Beam. You put the devices back to back, and they are used. NFC is used to bootstrap and other protocols such as Bluetooth or Wi-Fi Direct. There's a couple different frames that are used there. You have a polling request and polling response frame. Basically, when the connection first takes place, the reading device will make a polling request, and the other the device being read will make a polling response. And then after that, a transport frame is used. The frame layout is all pretty much the same, though. I believe it all usually will begin with a header of 48 bits of Manchester encoded zeros. There's two modes there, active and passive. Active is both devices will actually take turns acting as the reader, if you will. And passive is where they'll both generate the signal, take turns generating the signal. Passive is one device generates the signal and the other device modulates, all right, acting as if it was a tag, more or less. And then we have card emulation mode, which I said the mobile device behaves as a card itself. This can be done one of two ways. It can either be done with a secure element, where the secure element itself acts as the card, and it's pretty much just a pass-through right through the contactless front end, which is the NFC chip, straight to the secure element, and it will interact with the card reader directly. Or you can use what's known as host card emulation or software card emulation. This would be done if you don't have access to the secure element or don't have one. And in this case, your application processor will talk directly to the reader. And basically, you'll be doing this in software. You'll be software card emulation through an app, right? So not nearly obviously secure because you don't have anywhere safe, quote unquote, to put your keys. But if you don't have control over your secure element, like pretty much all of you won't have, because as we'll see, the carriers pretty much control most of the ways that you can use a secure element. It's a good way to be able to get around that. All right. Oop. What am I doing here? Okay. So a little bit about how NFC transfers data. One of the ways it does this, or one of the main way it does this, is NDEF, which is the NFC data exchange format. And what you have here is you have an NDEF message. It's basically, it's not such a protocol as it is a standard of encapsulating data. So you have your NDEF message. In that, you'll have one or more NDEF records, and those can be one of several different types. It could be a URI, text, different MIME types, or handover parameters for another kind of connection, such as Bluetooth, Wi-Fi Direct. And then inside the NDEF record, you're going to have the NDEF payload, and that is your actual payload. That's your actual data, right? All right. So the layout here, more or less, I don't think my little beam is going to work. Yeah, let me see that. Okay. So here we have our NDEF message. In that, we have one or more NDEF records. By the way, you can have as many NDEF records as you want, pretty much. There's no top end on that. Inside each of these NDEF records, you have a header and a payload. And then you have the type name format, which denotes what type of data it is, and then what type of record, rather. And then you have the ID, which is optional to use, and then the payload length. This header here, in the first NDEF record and header, pay attention to that when we talk about Android, because that's what Android uses to figure out what kind of app to launch on your phone. It reads the first one and figures out from that, more or less what app we should be using for this. We'll talk about that in a second. Okay, so just real quick though, some of the record types. You can see you have quite a few. It could be a smart poster, it could be text, URI, or different handover requests. And then we have the URI identifier codes here. So if your record type is URI, it's not just HTTP or HTTPS as we typically think of a URI or URL as. Excuse me, it could be mail to, it could be FTP or FTPS, SMB, NFS, Telnet, real-time streaming protocol, it could be SIP, it could be TFTP, or if you look down the end here, which is kind of neat, this is all different kind of Bluetooth stuff, right? So you have Bluetooth L2 cap, or you have TCP OBEX, Object Exchange Protocol, so, or just denote a file location. So you have a lot of different types of URIs that you can open, that you can request the phone to visit. So, all right, NFC on Android. I figured I'd talk a little bit about NFC on Android because it is probably the most significant implementation and has the most support, by the way, if you want to find out a lot about NFC. The Android Developers Guide is really, really good. It's really very detailed, and I am not an Android developer, but I can, very much understand everything that's It's very intuitive in the way that the code is laid out and such. So, and they're very descriptive. So anyway, mandatory on Android NFC devices. So if you're going to implement NFC on Android, you have to support NFC A, B, which is type A and B, F, which is Felica, Sony's standard or product, NFC V, which is the NFC vicinity, or vicinity cards. Now, you may have support on it in Android, but again, whether your chipset will read a particular type of card is up in the air. There's also support for it on Nokia phones for certainty. I'm not sure about others, but I do know Nokia has a guide related to it as well. I don't know if it is as fully implemented as it is on Android. Anyway, so optional is NXP's MyFair cards. Some of which are more NFC compliant than others. For instance, the MyFair Classic cards. As I said, if you do not have an NXP chipset, you're not going to be able to read them because of the fact that they use Crypto One, which is a proprietary NXP technology, rather than any kind of standards-based cryptography. All right, so NFC and Android. So basically, what I was just saying about the records is, so we read a tag with an Android device. It creates a tag object. Okay, and then it passes this to an Android activity encapsulated in an intent. So basically what it does is it reads the first record in the NF message and the header. And then based on that, it tries to figure out the best activity to handle it. So basically what it'll do is, first off, if you have an application in the foreground, something open on your phone, and it's registered to handle NDEF data, it's going to go to that one first. He's going to win. If there isn't, then it's going to look for applications that in their Android manifest.xml file have registered themselves as being able to handle NDEF data. So it's going to go with those guys first, one of those guys, most best fit. If failing that, it's going to fall back, and the function it calls is action NDEF discovered. If that fails, it's going to go to action tech discovered, where it will see, okay, is anybody registered to handle NFC A, NFC B, F, V, based on what this technology in use is. Failing that, it's going to fall back on action tag discovered. Now, action tag discovered is pretty general, so it's going to go by the type of tag. They recommend that you don't register your app under that sort of for tag technology, because you'll likely lose if any other app is registered to handle this. So now, failing that, if nothing happens, it'll open up the activity selector, and then you get that thing where it'll say, hey, what do you want to use to open this? It could be this, or that, right? As of 4.0, Android introduced the AAR's Android application records, so you can embed the package name of your app in the NDEF record, and then Android will launch that app when the tag's scanned. Failing that, if it doesn't have the app on there, it will open the Google Play Store and prompt you to download it. So, some of the tag types. There's 4 types of tags, type 1 through 4. Basically, the big difference between them is memory capacity, as you can see, and also whether they're like read and rewrite capable, and whether you can configure them as read-only, or they're configured by the manufacturer as being like read-only or read and rewrite. So you can see type 1 and 2, user can configure as read-only. Well, type 3 and 4 are configured by the manufacturer to be in one of those states. So if we look at some of the tag types here, all the tag types were based on an existing technology, an existing product. So type 1 was based on Innovation's Topaz tags. Type 2 based on NXP's MyFair Ultralights. The Ultralights are very cheap cards used generally for ticketing, like paper tickets, like concert tickets, like stuff you throw out. That's how cheap they are. I'll talk a little bit more about Ultralights and their security in a little bit. Type 2 is NXP's NTAG 203, which is another very popular tag. Type 3 is Felica, again. Then Type 4 is NXP's DesFire tags, DesFire EV1s. And then we have also the Smart MX. Interesting thing though, the Smart MX is actually what's utilized for secure elements in a lot of Android phones. And it is a totally, I guess you could say it's a computer within a computer. It has a processor, it has memory, it has its own operating system, which is the Java card operating system, and its own series of standards in order to be able to actually access it or manage applets on it. So it's a fairly sophisticated device. Then we have the NXP specific stuff, like I said, MyFair Classic, where they implemented up until ISO 14443-3, but on that fourth layer on top, they're using Crypto 1. So those are not totally standards compliant. So NFC, like I said, the tags are defined as ISO 15693. Communicates over 1356 megahertz, the same frequency as NFC, but it's not really, NFC per se, right? It is, one of the more significant, I guess you could say, deployments of it are what you're seeing in HID, what they're doing with CIOS right now, where your phone is acting as an I-class card. So that's a perfect example of NFCV. In Android, it's android.nfc.tech.nfcv as code support. Some of the tags are NXP's iCode tags and HID's I-class. I believe with the NXP iCode, you may have an issue there reading those if you don't have an NXP chipset. I'm not entirely sure, but I do believe that. There's also Texas Instruments tags fall under that. And then SD Micro, their Lyric family of cards also fall under what you don't call NFC vicinity. So peer-to-peer mode. You're putting two devices together, transferring data. It's more or less how the stack works out. ISO 18092 defines the bottom layer, okay? You could think of this more as a physical layer, if you will. The logical link control protocol, you could think of this as like the data link protocol or the MAC layer, okay? It is a data link protocol. Then on top of that, you're either going to have the simple NDEF exchange protocol, which is a standards-based protocol, or on some Android devices, not the newest, but I believe ICSM below, you will have what's known as the NDEF push protocol, which is an Android-specific protocol. It's a lot more simple and lightweight, but doesn't have the features that Snap has. As of Jelly Bean or ICS and going forward, they also went to they caved Android caved in and went with Snap as well. So LLCP, it's a layer 2 protocol. And then NF push protocol or Snap will ride on top of it for the actual data exchange. And what those will exchange is the NF messages. It has two service types, which is either connectionless or connection-oriented. So connectionless will be used if the higher layer protocol in use does its own reliable delivery, right? In which case, you don't need to do reliable delivery at 2 layers, right? So in that case, you don't need to use that. But if the upper layer protocol does not do its own reliable delivery, LLCP offers that functionality, and it does it by a sliding window, much like you have with TCP. The payload data units, PDUs, that are in use, the frames, if you will, are very simple. They're really only 5 fields, and what you'll see with like NPP and Snap, it's the same thing. They're only like 4 or 5 fields, and that's just the destination service access point, which is, I guess you could say, like a port, right? Basically, what LCP does is opens up a socket and listens. So you have in the field, you have a destination service access point, which is the address where it's going to. You have the PDU type, which is what kind of message this is, right? Is it a sync message? Is it a disconnect message? Is it a service discovery message asking the destination device what kind of services it offers? And then you have the source service access point, which is the source address. Then the sequence number, which is used for reliable delivery, and then the actual information that's being sent. And then other protocols will ride on top of it, not just Snap or NBP, but you could ride like the object exchange protocol on top of it, which you see used with Bluetooth commonly, or IP. The two protocols I can write on top of it, you have NPP, which is the NF push protocol. It's an Android-based protocol, not standards-based. It's used up until Android 3.2. And pretty much, it's very simple. Basically, in order to conform to their standard, you have to run a server. Each device that runs it has to run a server. And basically, the client connects to the server. It connects. It sends the NPP header, which basically has like the version number and then what kind of data to follow. And then sends the NPP header and the NDEF entries and then disconnects. That's it. It's just a push. It's like a unidirectional protocol, a one-way push. Snap is a little different. It's more of a bi-directional protocol, and it transfers via get and put messages. It also supports fragmentation, so you can fragment larger data units with it. And it uses the LLCP, Logical Link Control Protocol, the Layer 2 protocol. It uses its connection-oriented transport to do reliable delivery, so it doesn't do its own. So in this case, LLCP would use reliable delivery. By default, ICS and higher. And again, you see really it's like a 5-field frame. The frames are pretty much the same in the request and the response frames. You have the version, so that knows it's compatible with what it's talking to. Then you have either a request or a response, it denotes which it is. Then the length, and then the actual information. So you can see, like, it's not a very high bandwidth, high throughput protocol. So all the stuff that's designed around these protocols is try to be as lightweight as possible. So there's not a lot of fluff. Okay, so a little bit about hardware now. So picking a good reader and writer, right? You want to you want to have a few things. So libNFC, that we'll talk about in a minute, you want to be compatible with libNFC. libNFC is a library for NFC, hacking NFC, if you will, and most of the tools that you would want to use are based on it. So you want to be compatible with that. You want your reader writer to work with that. You want to be able to do card emulation. So that you can use your NFC adapter to emulate a tag. You want to be able to do peer-to-peer, so you can communicate with other devices. And you want to pretty much support all the major standards, right? So you want to be able to communicate with any targets devices when you're a reader that conform to the major standards. Also, you want to be able to abort commands and do things like cancel polling, and that's specific to peer-to-peer. And one of the issues with one of the readers, the ACR122U, which was a very popular reader, some of its forms were the touch-a-tag reader or the tic-tag reader. It's a great reader. However, there's been some issues with it working with NFC libNFC when doing peer-to-peer, where basically, since it uses I shouldn't say libNFC because it really works with PCSC, which is the Personal Computer Smart Card Library. It's just like an abstraction layer. And the PCSC really doesn't have the ability to cancel polling or abort commands when doing peer-to-peer. And because of that, a lot of people get a fairly frustrating experience when trying to do that sort of testing with that card. I actually did include that card in the presentation, though, because it's still a very popular card, and as I'll talk about, Charlie Miller did some very good work with it, fuzzing NFC devices for some research he did at Black Hat 2 years ago. So I figure it's good enough for Charlie, it's good enough for me. But on the nfctools.org, which is the libNFC site, there's a really good device compatibility page that lists a bunch of really good readers. So anyway, I know I'm getting a little behind here, so I'm going to try to speed it up a bit. This one is the PN532 breakout board. It's available at Adafruit. Great board, pretty cheap. It's like $40. Very compatible with all the major standards and does card emulation mode. And the cool thing about it is that it's very expandable. It's a really good chipset. It's really good if you have a Raspberry Pi. You can basically hook this right up to the Pi, and now you have a perfect self-contained unit for doing NFC hacking. So if you have a Raspberry Pi, I would seriously consider this board. And you can get it from Adafruit. And there's also some tutorials there about implementing it, what you can do with it, et cetera, and so forth. But this is a very good chipset, one of the most popular. This is the reader I actually have, which is the STM CL3711. It's an Identiv reader. I've found a couple things. Number one, it seems to be a very fast reader and very reliable. It also has full libNFC support and was the most recommended adapter to use with libNFC from the fellow that wrote and maintains libNFC. So that's a fairly ringing endorsement. The other one thing about this card that I found though is that if you are going to utilize it on say like Kali Linux or Backtrack, so I use it on Kali. You guys familiar with Kali? Pen testing distro. So anyway, Kali has a lot of NFC hacking tools built into it, which makes it a pretty useful distro for that, in my opinion. But one thing about it is that it will load, when you plug this device in, there's two things you want to do. You want to do an LS mod and then grep for PM533, and if you find that module loaded, do an RM mod at PM533 to remove it, otherwise it won't find the reader. The other thing you want to do is a kill all PCSCD to kill the PCSC daemon. Because libNFC and PCSC will fight each other. So if they're both loaded, you want to make sure one goes away. It's like Highlander, there can be only one. Hey, Highlander reference. Gladly. Oh. Doors. So anyway. Yeah, very good reader. I'm a fan of this one. And again, it's only like $40. So this one's like the unicorn. These guys, Milo Milosh, I can never remember this guy's last name, but he's forgotten more about RFID than probably most people, including myself, will ever know. Does some really awesome workshops on it, and has released a bunch of really great devices. This is a purpose-built device for RFID hacking, specifically 13.56 NFC hacking. The only downside is that their web store, which was supposed to reopen in August, did not reopen in August. I'm going to try to actually get in touch with these guys and find out why, because I really wanted one, because it's like a really, really cool device. A little more expensive at $60. The schematics actually are available on their site to build it. So if you are pretty good with hardware hacking, a little bit better than I am, you may want to give that a whack. Although I've considered it myself, and I would foresee some more soldering iron burns in my future. But yeah, if you can get your hands on one of these, I highly recommend it. And then, like I already said, the ACR122U, great car, I mean, very popular device. The only place you might run into some problems is with doing certain peer-to-peer testing. Supposedly the ACR122 USB driver corrects this somewhat, but they still, I thought it was kind of fixed, and then I read a post on the libNFC forum from the fellow that wrote it and maintained it. And he basically concluded with, this is why I don't recommend this card to be used. And this was only a couple months ago, so I guess it's still an issue. But at any rate, yeah, like I said, Charlie used this card when he did his NFC, Don't Stand So Close to Me, an analysis of the NFC attack surface, talk at Black Hat. So, yeah, good enough for Charlie, good enough for me. And then also the Proxmark 3. Proxmark 3, purpose-built RFID hacking device, supports not only high frequency, but also low frequency. You have to have an antenna for each, so you have to buy each antenna separately. But designed by Jonathan Westfuse, and really cool. I mean, you can sniff NFC with this. You can sniff card to reader, reader to card traffic, or read the cards with it. And some of the attacks against things like MyFair, one of the attacks was based on you being able to intercept traffic. So you can utilize that. A little pricey, but certainly worth having. And I believe there are, again, schematics available to build it yourself if you are ambitious. This one's,
That doesn't look like a DIY kind of card.
No, as I understand it, is not any kind of easy. But I do believe this stuff is available. I don't know what is involved, but not something I'd attempt anyway. But most of our guys use it for, our guys that do a lot of physical pen testing. I don't do a lot of physical pen testing myself. Apparently people say I look suspicious. But they use it for, is basically for cloning stuff like HID's prox cards. So basically, that's low frequency stuff, so it doesn't really fall into the NFC range, but the low frequency antenna looks sort of like a black CD. And what you do is you take this guy, stuff him in your pocket, run the wire down your sleeve, and palm the antenna. You go to the Starbucks nearest your target organization on Monday morning, and you wait for a couple of their employees to come in. Usually Starbucks is pretty crowded, so you're looking for the guy that hangs his badge on his belt. And you just get up close enough to him in line to just kind of give him a little bump. It's actually better to give him a little bump than just to kind of mosey up so close to somebody, because that sets off people's alarms. Anyway, so by able to do that, you're able to clone the tag. You take the tag and it stores it in the Proxmark. Then you can walk up to the reader and replay it back into the reader. This will get you into the building. Now, Brad, who spoke to me here last year, wrote a firmware upgrade for it, or patch called ProxBrew. And what this does is they found that in the Prox cards, there's like the memory layout goes like country ID, and then facility ID, and then user ID. And the user ID, or the employee ID, is not very long. I can't remember the length, but it's brute forceable. It's within a reasonable brute force range. So what you can do is, you say you're the employee that you've copied their badge. They have access to the building, but they don't have access to the executive floor, and they don't have access to the server room. So you take that, you get in the building, and then you go to the reader for the server room. And you put the antenna up to it, and it will cycle through that key space and try each option until it finds the correct key. Now, the only downside to this is it could take a little while. And number two, a lot of readers, when you get an incorrect read, will beep. So it can get noisy. Oddly enough, only one of our guys has gotten popped doing this. One of them actually got so bored of holding it there that he actually took the wire for the antenna and thumbtacked it to the wall over the reader and just sat down in a chair with the antenna hanging over the reader. Somebody apparently came by and asked him what he was doing. He said he was calibrating the reader. Noisy, isn't it? So, anyway. They'd say something, right?
You'd think.
So the guy that got busted, that is what happened. But what happened was, it wasn't quite that. It was they had an employee that had left the organization under bad terms, very bad terms. And they had his ID marked in the system. If this guy comes in, all hands on deck, right? So the one they hit that one,
Yeah.
and they came a running, boy. Yeah, he's like, dude, there was 4 of them on me before I knew it happened. You know? Yeah. So.
Good test.
Yeah. Bad luck for him.
That's a good security feature there.
Yeah.
Like a random number.
Yep. Yeah, he had the wrong number. It's like, what's the odds? All right, so a little bit more about hardware. So chipsets. The PN65N is what's in like the Galaxy Nexus. It's one of the phones I have. It is it combines the NFC radio, which is the PN512, which is actually the NFC radio, the contactless front end, an ADC51 microcontroller, which runs it, right? And then it has a built-in SmartMX chip for the secure element, and can communicate to the SIM card over single wire. We'll talk about that in a minute, because there's 3 form factors for secure elements. There's embedded, where it's either an embedded chip in the device or built into or in combination with the NFC chip. Or it can be in the UICC, which is the SIM card, or it can be in the SD card. So that's 3 ways of doing it. And the way to talk to the SD card or the SIM card, the practical way anyway, is using single wire. The way to talk to an embedded secure element is to use S2C, which is also known as NFC wired, NFC WI. Anyway, all right. So, to give you a little bit of the layout of how the chip works here. So the BN544. Let's start from here. Okay. So here's the contactless for the front end. This is actually the NFC chip here with the contactless front end. All right. Hanging off the side here, you see the SmartMX chip, which is the secure element, right? And then you have the hardware access layer. You have the microcontroller here. And then all this right here is known as the PN 531, I believe. One layer out, all this right here minus the embedded secure element is the PN 544, and that's the chipset that was like in the Nexus S and whatnot. So the only difference between the PN 65N and the PN 544 is that the 65N has an embedded, has a built-in, I should say, built-in secure element. What you have here with single wire is the ability to talk to a SIM card. It's a universal integrated circuit card, which is the SIM card. So if you have a secure element built into the form factor of a SIM card, you can talk over single wire with that. The HCI here, the host control interface, that's the interface back to the application processor. So that's the way back to the application processor. There's actually a standards-based version of that now called NCI that the NFC Standards Organization came up with. So they standardized it. Remember the NCI thing, though. I'll come back into play in a minute. So anyway, that's pretty much how they're laid out. So anyway, secure element, like I said, it's a tamper-resistant secure microcontroller, okay? It will actually, some of them, if you try to access them with the incorrect key too many times, it will just stop letting you in even if you have the right key. So the keys, you're not going to be able, I'm sorry. You're not going to be able to utilize it without your own keys. And the keys are generally controlled by what's known as trusted service managers. They are an intermediary, a middleman, I'm not sure what they really do, but they make a lot of money. Intermediary between the banks, the carriers, the manufacturers, and everybody that's involved in mobile payments. And they control the keys to the actual devices. So basically, if big bank A wants to implement an app that would utilize the secure element to store its keys or bank numbers, they would intermediary between them and the manufacturer and the mobile carriers, right? All right. So suffice it to say, you don't have the keys to your secure element, all right? The two secure elements that are controlled by the carriers are the embedded one and the one in the SIM card. The SD cards are not controlled by the carriers, obviously, but less and less phones seem to be coming out having SD cards. So anyway, communicating with the embedded secure element, it's done over STC, which is NFC wired. There's three modes of communication there. There's off, just off. Wired, where apps on your phone can communicate directly to the secure element. So basically, if you have an app that wants to store its keys securely and such, it can do that. And then virtual. In virtual, it does pass through to the contactless front end. And the secure element talks directly to the card reader. The reason this is, like you can say one way, is these elements can actually emulate cards completely. So like NXP's SmartMX can totally be a MyFair 1K, a MyFair 4K, and I believe some other cards as well. So it can completely, has modes where it can completely emulate a card and just be the card, be the card. No. Candy Shark, no. Okay, so couple more things about the other ones. So UICC, to communicate with the SIM card, the problem with the SIM card is the SIM card is not connected directly to the application processor. It's connected to the baseband processor, which is a totally different deal. You have to go to the radio interface layer, which uses AT commands. It's like a proprietary I2C interface. There's access, the Seek for Android toolkit actually provides a smart card API that lets you get access to it. However, some of the libraries that are in use to be able to get to it in the code on the phones are proprietary, and so if they don't add the code to them, which they haven't, you can't utilize it, right? So the other way of doing it is you can use single wire protocol if the NFC controller supports it to gain access to it. Same way you can get access to the SD card.
Quick question, how much time do I have? You're coming up on an hour here in 5 minutes.
Okay, so I just want to rock it, or so we're going to rock through here real fast. So as I already said, difference between the PN65N and the PN544 is that the PN65N has a built-in SmartMX chip. The secure elements, the SmartMX chip, particularly anyway, has its own operating system, it has a Java card OS. And then the actual interface and standard to install, remove, change, delete applets, which is what they're called, on the on the secure element is governed by what's known as the Global Platform Card Manager. And Global Platform was a standard that was developed by Visa, and now is its own independent entity, but they control, or the standard, I guess you say, they dictate the standard as to how you can do that, because each individual applet inside that secure element is its own entity, right? They have to be separate, right? Because in theory, at least, you'd have one from Bank of America, you might have one from Google, one from Chase, right? And they can't, never the twain shall meet. That's not what's happening right now because the carriers are so jealously guarding these things. But that's what should happen. Okay, so libNFC, already talked about. Open source C library for NFC. Most of the tools that you'll encounter will be written using this library. One of the cool things about it, though, too, is that it also has a lot of really great utilities. So, if, like on Kali Linux, you just type NFC- and hit tab a couple times, you'll come up with all these utilities for emulating cards, reading different types of cards, writing cards, right, what have you. So, really cool stuff there. Definitely something you're going to want to have. RF Idiot was written by Adam Laurie. It's the same thing. It's a set of Python scripts for interacting with RFID cards, not just NFC, but other cards as well. It works with libNFC and PCSC and will allow you to select which one you're using. So I would highly recommend that. You can find that on Kali by typing read and then hitting tab a couple times. And it will show you, it's like read MyFair Simple, read MyFair Ultra. Some of them are a little flaky, but by and large, they work pretty well. Okay, so some prior work on attacks real quick. Charlie Miller found a bunch of exploits, a bunch of vulnerabilities rather, in NFC and presented them at Blackout a couple of years ago. He also found a way to deliver exploits over NFC to a device and compromise it. MWR Labs did the same. They actually used two exploits, one to compromise the device and another to get, one to gain initial access to the device and the other for privilege escalation. Colin Mullner's done all kinds of different stuff. I would just take a look at his site. Dan Rosenberg found a bunch of buffer overflows in the Linux NFC stack. What he found it in was the NCI portion of it. Remember I told you of the HCI, those configuration interface, but it's standard based? At the time, it really wasn't used. So thankfully, at the time, it really wasn't used because these were real nasty buffer overflows. So MyFair, shot full of holes. The dark side attack is the most prominent among them, but there were many others as well. Couple things. Corey Benninger and Max Sabell from Intrepidus did a talk a couple years ago on cloning MyFair Ultralight cards. And then Bug Guardian Eagle this year at DEF CON followed up on that by finding that you could lock the one-time pad in ultralight cards. So what's up with, where is that? Did I miss it? Okay, let me talk about that real fast. Okay, so, oh no, I'm going to talk about that a little in the MyFair section, which you got to hurry to. So sniffing, MyFair NFC by itself doesn't provide encryption, so you can sniff it. One way of the ways of doing this is the Proxmark 3. Good way to do that. Wireshark has a whole bunch of dissectors in it for dissecting different kinds of NFC stuff. All right, another way of attacking, rewriting tags. So if your tags, like you're using in smart posters and other stuff in public for advertisement, are not locked, right? I can walk up to it with my phone, rewrite them, send you to my evil site, and then when you go up and you put your phone against it, it's going to send you directly to my evil site. On older on not even that much older versions of Android, it doesn't prompt you at all. On my Galaxy Nexus, it'll take me right to it. On my S4, it prompts me, but it also gives you the thing, don't ever display this again, please. So if you click that, which most people would because they don't get bothered by error messages, it's never going to ask you again, right? And most people are going to click OK anyway, okay? This is also used to erase trips from the ultralight ticket I'll talk about in a minute. Zero-click sharing, pretty much same idea. You can put two devices together and pop stuff open on someone's phone without prompting them. But obviously, you have to be right up against them. So their phone would have to be unattended. Okay, ultralight. MyFair Ultralight doesn't have anything in the way of real encryption or anything. It's utilized by a number of transit systems and also for paper ticketing like concerts and stuff, right? Because it's very cheap. All it has really is this 32-bit one-time pad. So figure it like this, right? What Max and Corey found was that, so what would really happen is after each trip you take on the train, you'd load your card up, right? You'd load up money on it, you'd pay money, and now you have all these trips. Every time you take a trip, you should set that one-time pad, one of those bits to 1, and you can't set them back. denoting that you've taken a trip and now you can't, you're running out of trips. What they found is that most of these places, most of these transit systems weren't using that. And so you could just make load up your card, make a copy of the card, read it, store it, and then once you run out of stuff, rewrite it, right? Some of these transit systems started using that. And then what Bughardy and Eagle disclosed at DEF CON this year is that they found these lock bytes on ultralight cards that'll let you lock different parts of memory, right? NFC cards or RFID cards are really just a grid of memory blocks, okay? As you'll see in a second. And you can lock any of those on there. What they found is that, hey, what if we use this functionality to lock the one-time pad? Yep, lock the one-time pad, and now when the transit system tries to write to it, nope, no good. Perfect. That, in a way, is what they get for using such a cheap card. It's not made for that sort of thing. It was not made to be used for this, but it was used anyway, probably because it was cheap. EMV, Electronic Visa, MasterCard and Visa Standard. This is really just a standard-based thing. You can read cards like this, cards that have a RFID chipset in them. You can read these cards. All you have to do is conform to the standard. There's a tool like PhonePass, and there's a couple apps available too. They'll read out the card number, your name, although sometimes they'll just say card holder, and the expiration date of the card. It won't read out the CVV number on the back because that's dynamic when used with this standard. PhonePass is cool because you can use it with a reader, but you can also use it with, if you get your hands on a VivoPay reader. I have one, but I lost the freaking power brick for it. I'm so pissed. But it's really cool because it's pretty cheap, and you use this on a laptop with the VivoPay to it, and you can read cards. Makes for a great demo if you don't lose your power brick. All right, so real fast, MyFair, because I know I'm running out of time here. So MyFair, again, developed by NXP. It uses, well, some of these are more standards compliant than other exercises. So let's run down the list real fast. MyFair Classic uses the Crypto One algorithm, was shot full of all kinds of holes. Terrible. Proprietary crypto, always bad. The Ultralight uses no crypto at all, but has those one-time pads. Ultralight C implemented triple DES. MyFair Plus is an AES 128 drop-in to replace the MyFair Classic. The DESFire uses triple DES. This was defeated by a side channel power analysis attack in 2011. So up until then, it was cool. The DESFire EV1 uses AES 128, and then we have the SmartMX, which we already talked about. So MyFair Classic. So really widely implemented by public transit systems. Okay, this is one that they were supposed to use. So it's standards compliant up to ISO 14443, but that top layer, that fourth layer, where ISO 14443-4 would be, it uses Crypto One. Crypto One has all kinds of problems. We'll talk about that in a second. So the way it's laid out is you have 16 bytes of memory. So, okay, you have a bunch of blocks. The sectors you have, in a MyFair Classic 1K, you have 64 sectors. Each sector has 4 blocks in it, and each block is 16 bytes of memory. It can either be a data block, which has data you can use for an access control system, or a value block, which you use in electronic wallet systems, okay? The last block of each sector is going to have two 48-bit keys and 4 access control bits. And then each sector is encrypted with its own key. The very first block of the very first sector is the manufacturer's block, and that contains the UID. And then you have these different protocol commands for the memory in there. And basically you can do things like read, based on your access control, what you're allowed to do. You can read, write, decrement, increment, restore, or transfer between these blocks. And it's laid out like this. So we have sector here, 0, 1, 2, all the way up to 16. So there's 16 of them. If you notice, each fourth block in the sector, there's 4 blocks in a sector, has key A and key B. They're 48-bit keys. And then you have 4 access control bits. It's actually 3. And then there's 1 unused bit, all right? And then the very first block of the very first sector is the manufacturer block, which contains the UID, which is a unique ID of the card, and some other information as well, all right? So these keys here should, in theory, you would be using unique keys for each sector, or you would not be using the default keys. There are a number of default keys out there, a whole big list, in fact, that were implemented. And as we'll see, that's one way to attack the cards. Okay, so real quick how MIFARE does its authentication. The reader. So basically the whole idea behind it is that the reader and the tag both want to make sure that each other knows the key. They don't trust each other, right? So the reader makes a request to the tag. Says, I want to read you. The tag generates a random nonce. It sends it to the reader. The reader generates its own nonce, and then it also encrypts the nonce that the tag sent it. Sends back that encrypted nonce and its own. The tag decrypts the reader's nonce and now knows that the reader has the key. It encrypts the reader's nonce with its own key, with the key it has, and sends it back to the reader. The reader then decrypts that, and now he knows, okay, the tag has the key. So now they both know they each have the key. This is at a high level how Crypto 1 works. So flaws in Crypto 1, I'm going to get too deep because, like I said, I'm running out of time. There's really low entropy. The pseudo-random number generator is only 16 bits, all right, so it flips really fast. There's a timing attack on the tag reader nonce because it's created only between the time it takes for the reader to power up and the tag to ask for a challenge. There is big time leakage in the parity keystream, or keystream leakage rather. It returns known parity error messages encrypted, so you have a known plaintext attack there. And then the parity bit and the first bit of the next plaintext byte are encrypted with the same key. So again, known plaintext attack. Then there's weaknesses in the cipher, like it only uses odd bits to generate the key stream. So that, yeah, so this reduces the key. Oh yeah. So this reduces the key space even further. And then you can roll back the linear feedback shift register as well. Also, not on the slide, but there's a implementation weakness where a lot of organizations where they'll maybe use the first few blocks, right? Like they'll use the first 10 blocks, 10 sectors on here, okay? And they'll nicely encrypt that with their key, their own key. But they'll leave the rest of the ones, unused ones, encrypted with the default key. Well, there's an attack, an offline nested attack, that one of the tools you can use to implement is called NFC. And what it does is you have to know one key of any one sector on the device. Using that, you can then get the keys for everything else on the card. So they maybe nicely encrypt those first 10 sectors with their own key, but they leave the other ones at the default because they're lazy. And you get one of those, this thing will try the default keys. There's like 7 or 8 of them. Finds that, boom, you're golden. All right. And this uses libNFC. If you by a chance, they're good people, and they don't encrypt any of these sectors or secure any of the sectors with a default key. CUK, which is the MIFARE Classic Universal Toolkit, I don't know what you think, implements its own as the dark side attack. It doesn't need to know any keys. It just takes a little while. So basically you tell it what sector you want to focus on. It will focus on that sector until it gets the key, one of the keys. Do you want key A or key B? Tell it, okay, I want key B from sector 1. Once it gets that one key, now I have one key. Now I go back to MFOC, and I get all of the other keys like that. And that's it. And that's why proprietary crypto sucks. This is also integrated in the Proxmark's firmware. You can take the Proxmark logs and use it in NFC UK, or you can do it directly in Proxmark's firmware. So I have made it to the end. I hope I didn't go too far over. Some recommended reading. BlackBerry's Developer Resource Center, really good. The Android Developer Guides, really, really good. Definite recommend reading there. The NFC form specs you can read here, and they actually are fairly readable, although there's still possibly a cure for narcolepsy. And then this blog, if you want to know about secure element and software card emulation, host card emulation, he did a 3-part blog series on this, and it's really, the guy knows his stuff big time. Great reading. And his other stuff on Android isn't bad at all, so highly recommended. Questiones?
So what do you know about the HTC One?
Not that much, honestly. I'm pretty much, I always had Samsung phones. I have a Galaxy Nexus, and right now I have an S4. My Nexus has the Galaxy Nexus has a NXP PN65N chipset in it, and an NXP NFC stack. My S4 has a Broadcom chipset in it, Broadcom NFC front end, and a Insight secure element, and uses Insight Secure's NFC stack. So the difference between those two also is that, like, my Galaxy Nexus will read MyFair Classic cards, but the Galaxy S4 unfortunately won't read them. Not only that, it seems to have to be a little flaky with a lot of NXP's cards. Even the Des Flyer, sometimes it has problems reading, which it really shouldn't. But I found like I have a bunch of different cards. If you guys want to look at them too, I have like the Samsung Tactiles, which are MyFair Des Flyer EV1s. It shouldn't really have too much issue reading them, but sometimes it does. So, at any rate, yeah. But I'm sorry. What is your question about the HTC One?
I just wondered what hardware it had.
I don't know off the top of my head. I think it might have the PN544 in it, honestly. Are we flying back? I think I had a couple listed out, but maybe only the Samsung ones. I apologize for something with a bit of a Samsung bias.
Way back.
Yeah, I think it was further back, right? No, not the first ones, dear. No, I listed the Galaxies. I can find out for you though, easy enough. So, if you want to know, it should be really easy to look up. If you just do a search for HTC One NFC chipset on Google, you'll find it. They're pretty much very good, easy to figure out what you have. So, yeah, one of the things that would be really cool to do some research on would be, and I'm planning to, is to look into how are these secure elements managed. You know, how are the keys being managed? How are the keys being transferred in order to get access to these things, right? There's got to be some way the keys are being transferred and managed in order to gain access to the actual card itself, right? You know, the smart MX and stuff. So it's like, you know, how is ISIS or, you know, Verizon and Google handling this? Google actually doesn't even use the freaking secure element anymore because of all the stuff that went down with Verizon. First, Verizon wouldn't give them access to secure element. So what Google did now is they don't use the secure element anymore. They don't use your credit card number. They use this like phony baloney MasterCard number that they all have that like on every phone. And then they transfer that to the reader. The reader finds it as valid, but then you have identifying information that contacts your account on the back end and verifies it's you, and then will then communicate with your actual account details. But they did that so that they could just do it all in software, using software card emulation, and get around the fact that the carriers, you know, AT&T and Verizon are trying to lock them out of the phones, right? But then the carriers actually went as far as to block the installation of the Google Wallet app from their phones. First, they wouldn't allow it on the phone. They wouldn't allow it to be downloaded from the Play Market. And then, you know, people obviously found a way around that by sideloading it on the phones. But then they actually changed the code so that if you sideload the app, it will say this app cannot be run. So you actually have to make modifications to the firmware running on the device in order to be able to utilize Google Wallet on your phone. So obviously it's far beyond what a normal quote-unquote user would do, right? Now a hacker's definitely going to do that because, you know, especially if it's like, I'm not allowed to do that. Oh, screw you! Now I'm definitely doing it, you know. But yeah, they're really like going above and beyond to be able to keep Wallet out of there because they have such a hard time rolling out ISIS. It's taken so freaking long, and apparently I hear it's a pile of dung that you know, they've been holding off Google Wallet all this time, and it has hurt Google Wallet. And overall, it has hurt mobile payments. So this sort of selfish approach is really set mobile payments back in the U.S. significantly. If you didn't have this sort of thing, I really feel if Google had not been prevented from having access to secure element on Verizon and AT&T devices, you know, we'd probably see mobile payments being, you know, 10 times more ubiquitous in the U.S. than they are right now. But as a result, you know, nada. No. Any other questions? All right, thank you guys.
Okay.